Right. So now we're going to cover a very important topic about spanning sets, which is basically a part of the feature transformation and representation learning. So we'll learn about fixed spanning sets first. So when they are fixed, and then when we make them learnable, how does this basically boil down to solving a matrix factorization problem across a wide variety of unsupervised learning tasks, including PCA, k-means, and also non-negative matrix completion. So let's start first with spanning sets. What are those? So first, before we dive into spanning sets, I want to make a hypothesis. So we are making a hypothesis about the data, that the data samples have been mean-centered, okay, for mathematical simplicity. And this is just for mathematical simplicity. And it's always nice and good to center your data, guys. So what does it mean, centering the data at the origin? It means basically, if you have your data somewhere in the space, you bring it to the origin, all right? And it is easily done by subtracting the mean from the data. So if I have, for example, this is a single sample right here that was, so let's put the original sample. Let's say the original sample was in this area, right? And this sample, let me just draw it well. So this sample is called xi. And to basically draw this sample to its current location, we need to subtract the mean. So it means that I take the vector xi, that belongs to Rg, of course, and I remove the mu, which is the average of all these points. Okay, so it's the average of the training points, and by doing that, and that, you know, like I get a new vector that is a new representation that is kind of centered. Okay, so mean centered. So it means we subtracted the mean, and you need to know that this is a d-dimensional vector because it's an average of all these d-dimensional training vector. And a very important point when you work on mean-centered data, that you guys do this separately for the training and the testing, which means when you have the training data, you cannot, when you have the whole data first, so this whole data x, n times d, you will split it into training part, okay, so train samples and test samples. Okay, so when you split it, you cannot take the mean from the whole data, which means, you know, if you have unseen testing samples here, you're going to include them in the mean. You cannot do that because this is called eavesdropping on the data statistics or distribution. You're not allowed to do that. Okay, so when you mean center, you need to do it separately for the training and for the testing. Or you can either, you know, remove, so first for the training, you're going to remove the mean of the training, which is the mu tr, but then you can apply this mu, you can take the same mu right here, which is the mu tr, and remove it for each sample. So you mean center the testing individually, independently, using the mu or the mean that you derived from the training. Okay, that's one way. Okay, you can also try to calculate the mean of the testing, but I would rather use the mean of the training because you don't know how many testing samples you'll have, and you want it to be generalizable. You want to test your model individually on each testing sample, and you want your testing samples to vary, right? So this is the right way of doing it. Okay, now after this hypothesis, let's start with the fixed spanning set. So what are those? So first, we're going to talk about what we call a perfect representation using fixed spanning set of a given data. So let's say, for example, right here in this example, we have a data set. Okay, so an xi point. So this xi point, we want to represent it as a, you know, like a multiplication of what we call a set of spanning vectors, a C matrix, and a set of coefficients. Okay, so you can write it in this way. So each xi, if I write this, if I expand it as a summation, I'm gonna get the sum from k to big K. These are the number of vectors in my matrix C, and I just multiply basically this vector by its, you know, the vector element by, you know, like it's the vector by the weight assigned to it to get xi. And ck basically is what we call the spanning set of vectors. So the image will get very clear here, guys. It's always good to have images. So let's look at this. This summarizes the spanning set for a particular sample. So let's say, let's denote this blue vector by xi, all right? So in this example, xi belongs to r d times 1, so or rd, okay? It's a d-dimensional vector. And now what we have a basis, a k basis right here of k vectors. So these are different vectors that form what we call a matrix, a big matrix C, and the matrix C is of dimension C belongs to R D times big K, all right? And then what we have, on the other hand, we multiply this matrix by a vector Wi, and I want to write it inside. So this vector Wi, so this vector belongs to basically RK, all right? So this belongs to RK, and from this example, you can see that what this actually represents is something really simple. We have a basis of vectors. This is our coordinate system. So in R3, we will have, we usually call this, you know, X, Y, Z, right? So it's an R3 space, and we have a point right here of coordinates, maybe 2, 2, 0, right? So 2, 2, 0. These are the coordinates. And the coordinates here denote W, so of our point I. So this is my point XI. And the basis basically is just, you know, the regular simple elementary basis. So 0, 0, 1, 0, 1, 0, and 1, 0, 0. All right. So you guys can see that in this example, this is a very simple example in R3. If we generalize this to k dimensions, to k vectors, we're going to have k dimensions. So adding more dimensions, like for this one, okay, different k's. And then we're going to represent every single vector or input sample as a multiplication of a basis vector or spanning vector set and a set of coordinates or a set of weights. So these are the weights. W represents the weights of or coordinates, right, of a point or a sample xi in the space spanned by C. What does it mean, spanned? It means that these basically, this vector basis defines my whole space. I can represent any point by different coordinates in the space of C, of the matrix C. So C spans, you know, a space, or sometimes we call it a subspace, okay? Defined by its spanning vectors, okay? Spanning vectors. Now we're going to see different cases. So this reminds you, this formula will remind you of so many things. We have seen this. Maybe the names of the variables change. Maybe, you know, what they represent change. What we are learning changes. But at the end, it's a very universal kind of formula. So let's go forward and see. So basically, this is, you know, like our point. So for each data point xi, we represent it using a new coordinate system. and a fixed coordinate system C. So C here basically is fixed or predefined. So that's why we call it a fixed spanning set. Fixed, it's not learnable. A fixed spanning set or predefined, okay? So we predefine it. So the values are fixed inside this matrix C. And then that belongs to RD times big K. And then what we want to find is the coordinates of my point xi in this new space, okay? So at the beginning, remember, our xi, if it lives in a, three-dimensional space, this is, xi belonging to R3. And now if I transform it, I'm going to define a new set of coordinates, right? C1, C2, and C3. And I will try to find the new coordinates W1, W2, W3 in this new space right here. Okay, so this is exactly what it means, right? So as if you're changing your dimensions, because look, we're going from, so in this case, by the way, guys, we call it, let me take one step back. So here, I'll explain once we get to the imperfect, but we call it perfect because we hypothesize that K equals D. And I will explain later why we call it perfect and when it becomes imperfect and why. So keep that in mind. So right now we're calling it K, but somehow we're saying that K is the same dimension. So we're just transforming, rotating, but we're not losing any dimensions from our original space. And the original space here is our blue space, for example. So we're still moving from somehow R3 to R3. So this is also R3, but these coordinates are different from the original ones, which are X1, X2, and X3. Like the coordinates, if we say that these are the coordinates of the first point. So anyways, like, how do we get this? So what are we after? We're after the W. So that's what we want to optimize because C is fixed, XI is fixed for each sample. So what is left for us to optimize? It's WI, right? And WI for every single sample. So we optimize that for every single sample. So which means we need to learn the WI for, all samples from 1 to n. Okay, if I have n samples. So if I have 100 points, I need to map these 100 points to the C space. And I need to get their, new coordinates W1 until, Wn, okay, in this new space. So 100 when n is equal to 100, right? So these are new coordinates. Now, what happens? So actually this notation, guys, is not really the best. So here, ideally, if I removed one, I dropped one coordinate. So it should be, if I write it properly, it should be point I, coordinate 1, I1, I3, all right? And then here I should have I1, I2. So this is the third, basically this is I is the sample. If I want to do it properly, I is the sample ID, the number, the sample ID, all right, or number. And then J, if I do X, IJ, J will be the feature position, okay? Okay, cool. So this is the proper notation that if we want to do it properly mathematically. So now, how do we optimize this function? So beautifully, this is a quadratic function, right? Loss function. So we have the L2 norm, it's squared, it's a quadratic function. So it's a least square loss, least squares, right? We've seen before, and it could be optimized easily. And when we optimize this, so I'm not going to go through the details of the optimization. So basically, we can use a first order in each weight vector WI. So you guys can also watch the videos. We have done a lot of first order optimizations. And this will give us a first order system, which takes this form. Okay, so we try to optimize to derive this with respect. So optimizing, derive this with respect to W, right? And it will it will get us into something of this form, okay? So when it gets us to something of this form, this is what we call a simple linear system. We have seen this in linear algebra. So basically we want to optimize the W, this is our variable, and everything else is a constant. So if you look at these for now, guys, these are considered as constants in this system, right? And this is also a constant. So this is an n by n symmetric system. So n here, sorry, like let's do a d by d. So here we have d is the number of features. So if we have d by d, if it's you know, like the number of features that we're having, symmetric linear system can be solved numerically. So we can solve this linearly and get the values for the wi. So the optimal weight vector wi star that satisfies this linear system. So let me just use a thicker line. So this one for the point xi, so we're getting the coordinates of each point individually, is referred to as the encoding. So now we're getting into new vocabulary. So this wi is called the encoding of xi over the spanning matrix C. All right. So what does it mean to encode? So it means that this, you know, new coordinate, these values in the new space, the coordinates of my point xi in the new space C is called encoding. So somehow I re-encoded my data into a new space C, and these basically are called encoding here. All right, so it will get clearer in a bit. So what is encoding? So the actual linear combination of the spanning vectors, okay, so the linear combination of the spanning vectors are these CWI. So right here is called decoding. So we have what we call a decoding process and encoding process. So in this example, let's look at this basically. So what we have here, we have a wi. So this is the encoding. These are the values of my points in the new space. Okay, so my point xi, I have encoded it in the new space C, in the new spanning space C. Okay, using these coordinates or these weights wi, and this is my optimal solution. Let's say I optimize the loss function that I had before. So this is my loss function. I get my w. And then in this new coordinate system, this is what I call as encoding. So now the decoding is actually when I project back this, you know, when I project into this space C, and this CW, the whole CW, all right, is called the decoding. So we're going to see visual examples. So I wanted to write this down, keep this in mind, and then we'll see several examples in a bit. So for example, so we have here original data, and this original data is represented, you know, using this space. So if we want to encode the data using C1 and C2, so this is C1, okay, and C2. And now we represent this into a new space. So now we take a new space spanned by C1 and C2. So we change everything, all right? So when you use this new space, what happens is that the distribution of the data changes. So in this new space, what we have, the encoded data, this point, the encoded data is actually CW I of maybe this original point xi. All right. So as if you're projecting into this new coordinate system and you're representing everything. So this was the C1, C2. You're representing it into a new space. And in this new space, things have changed. So they are more compact, more linearized a little bit. Here you can see that there are bits spread out, the points, right? So something has changed through this kind of, you know, simple transformation of this cloud of points synthetically created or made. Now, Let's move next. So we're going to revisit the encoding and decoding several times. So next, we're going to talk about a perfect representation using fixed orthonormal spanning set. So perfect, as I mentioned, K, we hypothesize that K is equal to D. All right, so that's what it means. So orthonormal, it means now we're adding a condition, right? So what is this condition? The condition is that the spanning set C1 to CK will be orthonormal. It means that in this case, the magnitude of each element Ci will be equal to 1, and two vectors are perpendicular, or they are orthonormal. So we have orthogonality of our space, which is beautiful because it makes things a lot easier to compute. So let's see why. So remember, guys, we had this kind of system to solve, right? And now what happens when we have, so I'm going to just copy this quickly. So we have this system to solve. And in this system, what do you know this? Now we have basically, thanks to the orthogonality of these, it means they are perpendicular, the C transpose C is equal to identity. So when, this is a mathematical property, by the way. So when you have a matrix which has orthogonal columns or rows, depending on how you take the transpose of the matrix or the original one. So if these are all orthogonal, right? So the basis is orthonormal, the spanning set is orthonormal of this matrix. Then when you do C transpose and you multiply it by C matrix, you're going to get the identity. And this is how you verify that the C is actually orthonormal. Okay? The very simple mathematical property. You can justify it. You can prove it. But this is a very well-known property. Now, what happens when we have this basically term becomes identity. D by D. If we have a D by D, right? Kind of matrix. So so here, if we take, so first we have this term removed. So we're left with only this term. So what happens with this term? It's beautiful. Basically, we have the C transpose Xi given us directly the encoding. What does it mean? Remember, guys, when we used to write L of W1, Wi, Wn, etc. is equal, and I want to optimize this loss over the number of, the difference between all of these guys, right? And I need to get the W, star, which is the optimal parameter. Now we can calculate it directly, right? It's explicitly written, which means I take my fixed set of spanning, this is fixed, as I mentioned. For now, it's still fixed. So it's predefined exactly as here. We predefine it, okay? So we define the values of our new spanning space. And then we simply can calculate it. So Wi is explicit, is cheaper to solve. We can explicitly write it. And so it's still the encoding, it's the direct encoding of our Xi into the new space. So here in this example, we can somehow relate this to what we call an autoencoder formula. So we took this CWIXI, right? And then what we're going to do is basically we will replace the Wi, look here, with the C transpose Xi. So in this example, remember the first formula, guys? What did we have in the first formula? In the first formula, we said we want to encode in the spanning set. So basically, we want a point, we want to represent it into a new space, right? And if the space is orthonormal, and we can get easily this formula. Now, this formula, we can plug it, because of the orthonormality, we can now plug it into this original, formalization of the new representation problem. And we replace the WI with C transpose XI. Okay, so let's see where this trick is taking us. Where is it taking us? So here, basically, what we are doing is what we call an autoencoding process. Okay, so if you guys have seen before deep learning, we have an encoder function, you have a low representation space, and we will see these in the future, and decoder function, and we have an xi, and we have an xi hat reconstructed. So in this case, what we're having is something like an autoencoder that tries to encode the same thing and minimize the distance between the reconstructed version of the same point xi. All right, so in this example, xi is first encoded via wi. So this is the encoding process, which is basically C transpose xi, and then decoded back to itself through the C. So this is the decoding process. So you can think about xi, which is the original sample, as being encoded using CT xi, so using CT, the transpose of the matrix CT C, to get us the WI, that is basically the output. And this WI, the new representation vector, which is this guy, right, is decoded through a matrix C right here that basically gives us the same xi. If it's identical, of course, if we're using the same dimension, we're going to have almost the same xi. All right, so that's the idea. So this is basically what we call the encoding process. And here, this part, it's, decoding. So we're decoding. So encoding and decoding, and we call it an autoencoder because basically what we have, like we're using the same C, the C, you can think about the C transpose and the C as inverse kind of mappings, all right? You map onto a space using the transpose of C, and you map back onto the same space using C, okay? So it's a self-autoencoding with these two beautiful matrices, C transpose and C, and this is what we call autoencoding because you're reconstructing the same thing. So autoencoding, you can read this differently. CC transpose xi equals xi. So basically, we're reconstructing the same thing through this transformation of spanning space. Okay, cool. Now, let's zoom out a little bit and read this. So basically, as I mentioned, so this becomes an autoencoder problem because we have the orthonormality. And so the encoding transformation CT and the decoding transformation C are actually, they are inverse operations as we talked here. Yeah, so the encoding CT and the decoding C, all right, very good. Now, we're going to move to the third case, and the third case, so we have seen the first case, guys, so remind me, we have seen, first, we started with the perfect case where we have a fixed spanning set, K is hypothesized to be equal to D, and then we move to a second case where we impose the orthonormality of the C. Now they are perpendicular, and we discovered that we can have the formula of the autoencoder, which is a kind of a self-supervised learning. So you don't have, you're trying to self-reconstruct the same thing beautifully using these two C transpose and C encoding and decoding matrices. And now we're going to talk about imperfect representation still in a fixed space, okay? So imperfect representation means that K will be smaller than D. So K is smaller than D. It means now we are mapping into a spanning space that has smaller dimensions or lower dimensions than the original space. So what does that mean? So it means that we can no longer perfectly represent every possible point in the input space. What does that mean? So look, very simple. You have a three-dimensional point. Let's say I'm standing, somebody's standing right here, okay? I have 3 coordinates. So I have a lot of information. I have a three-dimensional space. I know I'm moving in that space, right? And then I'm going to project my coordinates into a 2-dimensional space. So what happens? I'm reducing a 3-dimensional space like this into only 2 dimensions, which means I'm losing information. We agree on that, right? I'm losing information. There is a dimension that I have lost. So imagine going, for example, I'm going to give you another example. From R4, which is a video, for example, a video, to R, which is a scalar. So I am somehow mapping a whole video, okay, a whole video which has time as dimension. Let's use smaller, okay. So we have time here. We have, for example, the first coordinates, first dimensions x1 and x2, for example, right? And we're mapping this to R, a single scalar. So we lost a lot of information, right? We compressed a four-dimensional kind of signal into like this cube, basically. We map this cube. And we need to have another time. So 3-dimensional, you have time, need to have 3 actually. X1, 2, 3, and time. So that's in R4. So you have this cube moving. So it's a volume that's moving through time, right? 3 plus 1, that's 4. And then you're mapping it into scalar. So a lots of information. So here, this is the K, and this is the original D. And what happens, that's why we call that imperfect representation into a new spanning space that have less dimension, okay? So now what we hope is that, with a new representation, with a new spanning space C that is of lower dimension K, smaller than D, that we can still approximate well the original data set. So we can approximate it. It's an approximation. It's not an equality anymore, okay? So now we move to the next space. So let's look at original data encoding, decoding. So in this space, we go, for example, into 2-dimensional space. So the original data looks like this. So it's a 3-dimensional space. We all agree on this, right, guys? So we have a 3-dimensional space. And then what happens is that we're going to create a spanning space where we're going to encode the data. And this spanning space, we have CTW, P for point B, okay, point XB, for example. And this is the encoding. So we're encoded the data. And here, basically, this is the W that is CT, that actually is the WP that is the projection onto C. So basically CXP, right? So this is what we call the encoding of XP. So in this new dimensional space that is spanned by these 2 vectors, C1 and C2, right? We move to R2. We have the new coordinates. So all our points right here, guys, all our points have been projected into this new space, okay, new space where we can easily represent, the points in right here. So this is a distribution of the points where we projected each point onto this new subspace. It's a new subspace that's called subspace, okay, spanned by C, which is equal to C1 and C2, all right? So now, in this case, what we have, we're going to, encode the data. So this is what we call encoded data. So the data is encoded into 2-dimensional, lower dimensional space. And then if we want to decode the data, what happens when we decode? So when we're decoding the data, we drop XP perpendicularly onto the subspace spanned by C. So when we drop it perpendicularly right here, right? So we decode the data. And when we decode it in which space, guys? Into the original space. So here we decoded the data into the original space, and you can see the representation of the data into this space. So what happens in this case, what happens is that now I have the decoded data right here, but I need to calculate my error. So the error that I'm making in my reconstruction, what I'm losing actually is all of these, right? So these are my errors, because right now I am representing my data into a two-dimensional space, and I'm like kind of building back the original space. But when I'm building back the original space, the points have moved because now I'm using that, like decoding part. I'm decoding the data, but when I'm decoding it into the original space, somehow I transformed the relationship between the original points, because here I have projected them, okay? So basically, I'm decoding what I have encoded. I'm not decoding the original ones. And this is, how all encoding, decoding neural networks work. So basically, you try to learn a mapping function, see like an encoding and a decoding function. And once you learn these, whether they are inverses or not, it depends on the case, right? But at the end, the idea is that we have original points, we want to represent them into a lower dimensional space. And it happens that when, like we define this space right here, we get these new coordinates of each point encoded by WP. So these are the new coordinates in the new space. And you can see it this way also. These are the new coordinates in my new space, right? So, all right, cool. So, and now I think what we can move on to the next. If you guys have any questions, please let me know. If anything you're struggling with, so you may need a bit of time to kind of wrap your head around geometry. Yes, Haitham.
Just one question. How K is a particular perpendicular? It is an autoencoder. How can I explain more?
So how K is
how? When K is perpendicular, it is an autoencoder. Mathematically, how?
When K is perpendicular, it is what? Sorry?
It is an autoencoder. It's here. The descent is
yes,
below.
it is an autoencoder. Yeah. So like basically here, because look, when it is perpendicular, we get this formula, right? So look, when we started off, we started with these, and when it is perpendicular, when C is orthonormal, we get this formula right here. So because we get this formula right here and we plug it into the original one, so when we started with spanning sets, so this is what we have. This is the formula, right? So when you have, an orthonormal basis, basically Wi is equal to CT, XI. So basically what you're doing, you're replacing Wi with CTXI. So somehow you're getting rid, you're not even having the W anymore. You're doing a sort of a self-encoding, right? So it's the same thing right here. You're encoding it and then you're decoding it. So it started with this basically, with this the very first formula, and then how we got the the Wi is equal to C transpose XI. And when we've done that, we are able to kind of, express the Wi as a function of the C transpose X, XI, and then you get the these autoencoder formula that we have. So this is the one right here. So when you get the notes, I think you can go over that again, but this is the formula that we got. And the first part, as I mentioned, is the WI, which is we call the encoding, if you guys remember. So this is the encoding of the point, the encoding coordinates, and then we basically decode what has been encoded. So we decode back into the original space. So this should map us back into the original space. Okay. So in linear algebra, if you write this, you expand it, you should have this in the this part, you should have it, the encoding part should be in, for example, in R2. And when you decode, this part should belong to R3 because your original point belongs to R3, right? So everything needs to make sense when you do the mathematical, the algebraic illustration and representation, illustration of this, I mean, in terms of matrices and vectors. Okay, so I hope it's a bit clear. I know it's a bit heavy. So once we go over the summary map, guys, I made everything clearer so you can see the whole picture, and it's a lot easier than having things, just going through the lecture notes step by step. So we're building a story here, but once you overview everything, you're going to gain a lot of clarity. So it'll become clear to you. And if you have any questions after I share the map and explain the map to you, please note them all down. And I'm happy to take all of these questions in the following session, all right, if I can answer them immediately. All right, very cool. Now, so we talked about that now we have an imperfect representation. So an imperfect representation is because K is smaller than D. But what if we have also K is orthonormal? So as I mentioned earlier, the autoencoder becomes like this. So we have CC transpose, XI, and it's almost equal. So before that, look, guys, before that, we have an equality, right? So it is equal. Why? Because we're preserving all dimensions. So K here is perfect, is a perfect case. So K is actually is equal to D. So in this case, K is equal to D because we have perfect case. But when it becomes imperfect, then even when we have orthonormality, we still have the same autoencoder formula, but we may not reconstruct this fully exactly the same because remember, we're going from R3 to R2 and back to R3. So when you do this kind of transition, you're losing a lot of information when you decode back. And this is shown exactly here, guys. So this is a lot of loss of information. These are all errors that I'm making when I represented the points in the decoded space, original space right there. So you can see it even visually. So basically that's why it's a semi-equality. So we hope it to approximate its own reconstruction, but you will not get the perfect reconstruction because you're removing the original dimensionality in the embedding space. Okay, cool. Now, I have a question for you guys. Is C transpose, the encoding function, still the inverse of the decoding in this example? Yeah, no, very good. Not necessarily, because we don't have an equality here, right? So the answer is no for that. Now let's move next. So now we covered all the fixed set. So if we go back quickly, so we covered, we covered this part. So the fixed, perfect case with orthonormal, imperfect case, including also orthonormal, which is an autoencoder basically. Now we're gonna move to the next step, which is the learnable fixed, sorry, it's not fixed anymore, the learnable spanning set. So let's see what happens when this becomes learnable. So we're gonna move forward to basically this right here. All right. So when the spanning set becomes learnable, now we're not given anymore a fixed set. So we are giving a set of vectors, and we want, of course, the data is still mean-centered. Okay, as I mentioned before, the data is mean-centered. But what we aim to do is to learn the C, because now the spanning subspace is not fixed, right? The C vectors, the basis of my subspace, my new space where I'm going to transfer my point, and hope that my point will have a better representation in that k-dimensional space, better than the representation it had in the original space. Like, for example, when I go back to the image of the dog, I don't want to represent all pixels in the image because not all of them are important. I want in my new space to represent the discriminative features of a dog. What makes a dog a dog? Maybe it's the eye or nose or size or like, you know, like things, numbers that my model will extract in this new space. When I define my new space, I will be able to have a better representation of what a dog is, okay? So here we are after two things. So we're not after only the W, which is the encoding of the samples, like the coordinates, the weights of my sample in my new space C, but we're learning C. So we have two, basically we have two big matrices or two big, two different types of variables to estimate the space and the coordinates in the space at the same time. So think about it, guys. If we have a space, right, like this, right? And this is the new space C. So we have C1, C2, C3, until C big K. So I have a point somewhere in my original space, and this was even higher dimensions, all right? This is my point xi. So I want to represent my point in my new space. So first I need to define the space. I need to find these vectors, these basis vectors. I need to find the spanning set of vectors. First, I don't know where the vectors are, have no idea. So it could be here, there, have an infinite number of possibilities. And the second question is like, let's say we have fixed the C, we're happy now. So okay, so we fix the C, so we have our transformed, like kind of encoded, function and encoding of this in the new space, CTXI, right? So if I'm encoded it using WI, so the problem is like, I don't even know where WI is. So it could be here, there. So once it's fixed, I need to optimize the W2. So you have two things to optimize. You need to optimize the space itself where the point will exist, and you have to optimize the coordinates of the point where it's going to be located in the space. Good? So far, so good. So this is very important because we're going to get into matrix factorization in a bit. So now everything becomes learnable, and it's even harder. So for example, I'm going to give you a few examples of this, but this is also another illustration about the original data. We're living in an R3. So R3 is spanned here by x1, x2, x3. And then we map it into two-dimensional space. These are the C vectors represented in the original space, right? So we find them, and then we define them here. And then we basically encode, so you guys can see that the data is mean-centered right here. And then we decode the data onto the original space, so we project into the space spanned by C1, C2. So this is what it means, it is spanned. So when you have a space, if you think about it in two dimensions, your vectors will define a hyperplane. So this is my hyperplane that is defined or spanned by my two vectors, C1 and C2. So, okay. And then here, this is a flattened representation of my space because now I'm using just C1 and C2. So we just flatten it, we're represented there. And then we go back to this and we project all these points into this space. So this is the decoding. The decoding will happen. It is in the original space, but what I'm going to show is actually the coordinates of these points that have been represented in this space. So I'll do it like this. So this guy is actually this guy. It's actually this guy over here. And we have points scattered all over below and up. But we're trying to find the space that approximates these points best, okay? So if I have a hyperplane, let's say, I'm trying to optimize, and I have a hyperplane like this, and I put C1, C2 like that, this is not a good hyperplane. And if I project my data, I'm going to have a lot of mistakes, right? I'm going to have a lot of mistakes here. So that's not good. So that's not a good hyperplane. So this is why this subspace is learnable. So we need to optimize it. We need to get the best C star, okay? Cool. So now we're going to talk about, so we talked about linear autoencoders. And right here, we'll go back to that. So now everything becomes learnable, which means in this linear autoencoder before, we did not mention that we can learn C. Now we can learn the C itself, okay? It's not predefined. So we're not encoding and decoding using a fixed set. We are making C learnable. So we need to find this subspace where we're going to encode, then decode the data. So basically, this boils down to optimizing this, squared loss function. It's a quadratic loss. And we have two variables here, as I mentioned, the space itself, the spanning subspace, and the coordinates in the space of each point I over the number of training points, okay? So now, because we have, as I mentioned, orthonormality, right? Because K is orthonormal, then WI is expressed as C transpose XI. We have seen this before. And then if we replace, we're going to get this beautiful formula, which is basically now, how many variables do we optimize if we have K orthonormal? If K is orthonormal, what do we need to optimize here, guys? C, right? Only C, yeah? So we only optimize C. So basically, it's very nice. We completely downsize the optimization problem. We don't need to optimize the WI when we have orthonormality. That's why orthonormality is a beautiful, I would say, mathematical property to have in a spanning space, because it makes the computational problem less expensive and costly. So you end up only learning a single matrix instead of matrix and a bunch of other values. All right, cool. So now this is the autoencoder loss function. And now we need to learn the space where we can encode and decode at best. So encode and decode at best, it means when I encode XI and I decode XI, okay, I'm gonna get an XI hat in the decoded original space, the decoded XI in the original space. And I hope that this will be very close to XI. So you can see, guys, the errors, as I mentioned before, so visually also. So basically here, we learn the encoding and decoding mappings instead of prefixing them, as I mentioned. And C has a perpendicular basis vector. So that's why we have this kind of beautiful formula, and you can memorize this for an autoencoder that is orthonormal, if you can justify, if you can enforce this property when you learn it. All right, so cool. Now this is an example, another example. So just to go over different examples, so you guys should be able to imagine that in your head to do the projection, the encoding and the decoding. So the encoding process in this space, so I have only one C1, and this is my C1 basically, right? And if I project all these points onto this single line, so if I put the line right here, and it's over here, right? And you project everyone, you're gonna get these points. So when I project, what does it mean? That means I get this point, I project it. Sorry, let's use this one. And I get this point. So then I project, I get these bunch of points, right? And then these are my points right here. So you guys can see them. And when you decode back into the original space, but what you decode is the original data. So basically you're gonna end up with the representation of this data onto this line, and that's what we call the decoding. So projecting and then visualizing into the, mapping back onto the original space, the two-dimensional, and you'll have this representation basically. And you can see that you have some mistakes, a lot of mistakes, actually, these values. And if it's a squared loss, then you're gonna have, like squares, like basically adding a lot of squares of errors, which is not good. So now let's move next. So the solution of the linear autoencoder, by the way. So when we say that this is a linear autoencoder, and is what we call principal components, pointing in the data sets larger directions of orthogonal variance. So it turns out, guys, that the linear autoencoder with orthonormal C is exactly PCA, right? So this is exactly the formula. If you want to solve this and you write DL with respect to DC, right? And I recommend that you guys watch lecture 14, Blink 14. So I talk about PCA from 0 to 1 with all the math behind. So you can link it up to this one. So as I said, I'm not going to go into the math of this because it's been covered elsewhere. Otherwise, it's going to take another hour, 2 hours, even more. So basically here, what we discover is that the linear autoencoder solving this loss function will boil down to finding basically the eigenvector decomposition of the covariance matrix of the data. So this is what PCA is for you who know PCA and who have taken PCA before, principal component analysis. So let me explain again. So if you solve this, if you optimize this, right? If you start optimizing and calculating the derivatives with respect to the variable C, you will find out that the optimal, actually what you're looking for, your C space is simply the eigenvectors. The C is actually the eigenvectors of the data covariance matrix. And what is the data covariance matrix? So this is the, all of you should know this, by the way, because a very important fundamental. So we have endpoints. So this is sample 1, and this is sample n. These are the number of features. And when you represent the matrix in this way, d times n, okay? So this is rd times n. And you take the covariance, which is basically 1 divided by n x transpose. This is how you write the covariance. And the covariance will belong to R. What is the size of the covariance, guys? Can you write it down? Double check. Again, so let's see. Let's do it together. Let's do it together, guys. Let's do it together. D times n, and the transpose, what is the size of the, what is the dimension of the transpose? When you transpose the rows and the vectors, you flip. So the original x is d times n, so the transpose is n times d. So the covariance is d times d, okay? So it's d times d. Thanks for the participation, though. So it's d times d, guys, okay? So why? Because it's the number of features, the covariance of the features. And this is why we call a feature, I think this is in lecture 3 also, we call a feature a covariate, okay? Because the dimension of the covariance matrix, which is this matrix, okay? So this whole matrix is of d by d. So we see how two different features, feature, for example, I and feature j, they co-vary across all samples. And if you guys forgot how to calculate this and the meaning of that, the relational meaning of two covariates, I think you need to kind of refresh your memory about covariance matrices, because we're going to see them everywhere. They're very powerful. Covariance matrices are in PCA. We used, part of them, and also in SVM and other optimization problems. So it turns out, interestingly, that the solution of this linear autoencoder is basically the eigenvector space. So the C is the eigenvectors of the covariance matrix. And the W is actually the eigenvalues assigned to this matrix. So this is what we call eigen decomposition. So decomposing a matrix. So if this is a covariate, if we call the covariate Z, right? So this one, this whole covariance matrix, right? We will decompose it into a vector space V's and also coordinate system D, right? So the eigenvalues. And this is how we define PCA. And it turns out that PCA is also is sort of, interestingly, another factorization problem right here. So it was derived from a CW originally, which is a factorization problem. All right. So now I'm going to give you, I'm going to ask you an example. So can you think about a case where the data distribution causes PCA or linear autoencoding to fail? Can you think about a case where linear autoencoding would fail? So what do we do in linear autoencoding? We represent the data into a linear space, right? Okay. So can you think of a scenario or a case where you cannot actually do so? Like you can't project all the data properly into a single line. You can start with this one. Like here, this is a nice example where actually the data can easily fit into a space spanned by one line when you project, right? Can you think about an example where the data distribution or location in the original space would not allow you to project it into one single nonlinear space? One single linear space. So let's think together. For example, oops. So if I take the original space like this, and then we have a bunch of points. So let's say these are my points. And I can find the PCA is actually, if you look at the variance, it's the eigenvectors, or they maximize the variance of the data. So let's call this C1, C2. These are the principal components. And this works fine because you can map it onto a single space and project it into this space spanned by C1 and C2. Okay, so this is your space. So project everything onto that space. Now, what happens when you have something like this? So when you have points that look like this. So these are all your points, the green and the purple. So this will not work out in this case, right? Because what happens in this case is that we have two completely different subspaces. So you can't have a joint covariance, because if you have if you look at the variance of the data, the data is very, sorry, keep on using the wrong one. The data is very variable, right? So it's all this space. So it's not good. So if you're going to get a C, you're going to get a C maybe that maximizes the variance. So you're going to have something like this, which is not really good and representative, right? So basically PCA dramatically fails when you do have what we call the data lies on different subspaces or different linear spaces. So this will not work out. And you can see it here in this example. So basically PCA fails when the data does not live in a linear subspace. So for example, you have the first data right here. And then you have the second one, okay? And when you project onto single lines and you try to find the covariance, and you take the covariance of this and you one dimensional, it's going to take probably the mid of this distribution, right? The maximum variance is this direction. What does it mean, the maximum variance? The maximum variance means, guys, which direction your points are, in which direction your points are mostly spread out. Spread out. This is the breadth of these points. They're spread out along this direction. But if I take another direction, so let's try to understand the maximizing the variance, remembering that at least, okay? So if I take this direction, is this a good direction? So if I look at my points and I project them into this direction, right? This is their breadth. Okay, this is delta. When I take these points, also, this is another delta. So this is delta 2, delta 1 for the blue and the oranges. But if I take another direction, so let's say the black one, right? And I project my points, I see that this is my delta. So I maximize, this is a maximum variance, right? And this is also, this maximizes the variance of this second set, which means the PC1 is the eigenvector of the covariance of the data formed by the blue points and the data formed, the same data, including these two cloud of points, right? The orange and the blue will be directed by this one because this is the best direction that maximizes the variance of the data. Okay? Intuitively speaking. And as I said, if you guys forget this, you can watch Blink, 14. So here, if you project, when you project, what do you guys notice? That this space is not good because actually these points are very separable. They're not the same, but now we're mixing them. So we have confused or overlapped completely two different classes or completely two different subspaces and collapsed them into a space where we're not representing them well. All right, cool, great. So now, do we have any question? Haitham, you had a question. I saw your hand up.
Just I want to say if the PCA fail when the plane is not Euclidean, the space is not Euclidean, and we have main fault. The space
Yes.
is not Euclidean, and we have a main fault, so the PCA will.
Very good. That's exactly the same. So a subspace is actually, it's also called a subspace. Sometimes we call it a manifold, which is a high dimensional space, which means, the data lives on a curved space. Okay. So this is a manifold, and the manifold can be linearly approximated. So it depends. So a manifold is a nonlinear, could be also, it's a nonlinear subspace. But if you for PCA, you need a linear subspace, okay, linear subspace, which means your points, look, so it's a very good reminder, thank you. So your points will be scattered. So we have a few points here maybe, and we have, the data set is located in different parts of this manifold, okay? And then what happens is that if you only have a part of the manifold, you want to approximate it by a linear subspace. So imagine projecting all of those into a tangent plane to this highly curved dimensional surface, which is a manifold, okay? So you're projecting as if you are on top of the mountain, and you're projecting, or on the side of the mountain, and you're projecting everyone onto the closest, most, the tangent hyperplane. So this is, subspace, and once you do that, you can do maybe PCA. The problem is that when you're having a highly curved, manifold, and your space in nonlinear, which means your data is located in a completely nonlinear space. So you go hiking, you go from the top of one mountain to a valley, and then to top of another mountain. And then if you want to create a linear subspace that approximates all of those, you're going to have a lot of errors, because when you project, you're going to have a lot of big distances, because it's a highly nonlinear complex manifold, right? So it won't approximate your space. And what we want our C to be a good approximation, right, of our original data, of original XI. So if it's not a good approximation, then it's really a bad new space to create or to learn, right? But yeah, so anyways, as I mentioned, so PCA or linear autoencoders, they live in a linear, so they live in a linear subspace. So when the linearity breaks, the model breaks. So here they're not linear dependent. So you can see there are two different linear lines, right? So you cannot fit a line into this these two altogether. All right, cool. Good. So now we're going to see another example, recommendation system. So matrix factorization is very important. So another example here. So let's say for example, you're using Netflix or using Amazon or any kind of mobile app where you have a bunch of users and they have a bunch of products. And here, for example, it happens to be movies, right? So you see a particular user's ranking particular products or particular movies, and your goal is, as a vendor, is to sell more products, maximize profit. So ideally, you would guess which products your customer 7 will like most, right? So what you're going to do, you're going to predict the ranking of this user to these unknown movies. So user 7 did not see movie 2, but you would want to guess if this movie will be a 1-star, so you can eliminate it and not recommend it or suggest it to the user, or it could be maybe 3 stars and you will suggest it to the user and the user will spend time watching it, so that will maximize your profit. All right, cool. So this is what we call a matrix completion problem. It's a whole area. You can study books. There's books of optimization and lots of variants on matrix completion. You can spend days learning this, not weeks. So matrix completion, we're going to just look at the basic foundation, but there are lots of variants, right? Lots of complicated variants, but we will start with a simple form, which is a recommender system, as an example, a toy example. So here the goal is basically, guys, to complete, as I mentioned, the missing ratings to recommend movies for users. So let omega denote the index of the non-empty entries of xi. So non-empty entries, it means my omega will basically mark all of those non-empty. They have ground truth data. So I have ground truth data and observations in my omega, right? Now, omega basically I is, here is the jth entry of xi. So when xi is filled, all right, of the ith customer rating vector, and when we have d possible products. So what it means that, so xi is the customer, so I is the customer, and omega I is the jth entry, so this entry. So here are the index, so omega 4 is equal to index 2, because only one is filled out. So that's easy. So now what we want is we assume that some ideal spanning set of k fundamental taste vectors. So what it means, like, for example, we have a particular set of movies, okay? We call them the spanning sets, and these are movie types. So for example, romance, horror movie. So we call them taste vectors. And these taste vectors will represent the new space. So maybe you have millions of movies, but these millions of movies, so for example, here, all right, I want to put D here, it's better. And here, the number of samples, I want to put N. All right. So let's say you have D movies, D is 1 million. So you want to bring this 1 million space to a small set of movies, movie types, that is what we call them, taste vectors, depends on the taste of the viewer. And this will be an R4, or, just 4 types of movies. Like, for example, rom-com, comedy, comedy romance, for example. And then you have horror movies, you have different types of movies, okay? So what you're doing is you're mapping a d-dimensional space with 1 million movies to a 4-dimensional space, basically. So this is very interesting, right? So as an engineer, you can actually use this for an app, which is really cool. It has been used, by the way. So these simple models really kind of work out and give you some good guesses. So now we can package in, as I said, we can package these vectors, the taste vectors, into D times K C matrix. So this is our new spanning matrix. And we can express, you know, like basically a new rating as a projection, okay, as a linear combination or projection into this new space that we want to learn. So that's the key idea here. And yeah, so xi actually is the rating that we want to predict, right? Rating vector of customer I, right? Cool. So now if we want to solve this, this could be you know, defined as a factorization problem. So you want to learn the weights, right? So you want to predict these particular ratings, but you want to you want to optimize what we call it the same squared loss, but over the ground truth. So why we optimize over the omega I? Because omega I is what we're observing. So we're trying to reconstruct every single xi right here as a linear combination of a c that we want to learn and a w that we want to learn also. And we are only optimizing over what we observe. And this makes sense because you cannot optimize over the missing values. The whole point of matrix completion is to predict these values. Okay, cool. So now I'm gonna speed up a little bit, guys, because I know many of you are like getting a bit tired. So we'll try to kind of wrap up maximum in less than 15 minutes. So take a deep breath. Do you want to get a sip of water or something? I will take some water here. I'm happy to take your questions. So we're gonna take I think we're gonna do k-means quickly, and then the generalized factorization, and we're done. So I'm gonna leave this part to the next. It's based on a beautiful paper. It's actually very small. I mean, like, well, it's 2 pages-ish. So I'm gonna stop right here after we finish the 2 left cases, which are k-means and generalized matrix factorization.